Good morning, everyone. We're quickly going to take a look at our current understanding of the key ingredients for the world-class orogenic gold systems that we see preserved in the Bendigo zone of Victoria. The geological characteristics of these systems has been intensely studied by industry, academia, and the Geological Survey of Victoria over the past 170 years. So they actually make pretty excellent case studies for mineral explorers in the state who are dealing with both the current challenges of exploring under Murray Basin cover, but also expanding search horizons into other tectonic stratigraphic zones across Victoria. Together, these ingredients will help us actually understand why Victoria is responsible for 2% of the world's gold production that is come from only 0.00004% of the world's land surface. We're going to start at the end, and here's the key ingredients to the Bendigo zone gold recipe. Some of these, like tectonic triggers, physiochemical traps, and preservation history, are pretty similar across other deposits in Victoria. To form economic concentrations of gold in a deposit, we actually need a series of geological events, processes, and environmental conditions to coincide in both space and time. We've got evidence in Victoria that gold was mobile and became concentrated during at least 3 phases of orogenesis and deformation related to transient 45 and 380 MA. GSV, the V-shaped fault geometry of first order crustal scale faults with opposing dips in the Bendigo and Stool zones, and that there are a series of inflection points where they transition from relatively flat-lying structures to steeply dipping structures, and it's during deformation that these were the actual key to transitioning from structures that were relatively open to ones that were relatively closed, and this generated a series of fluid escape structures, up second order structures, and those are the ones that exert a strong control on the distribution of well-endowed gold fields. In terms of gold sources, there's 2 really good candidates that dominate Victorian geology across most of the Lachlan Fold Belt. Although it's controversial which one is actually key, and the orogenic events provide plenty of scope for metamorphic fluid generation at depth to provide a transport mechanism from the metal from the source to trap. At the deposit scale, we see that physiochemical traps for mineralization occur where they're relatively flat portions of faults intersect with fold axes, and these represent dilational sites during transpression and compression. This generates a structural trap for mineralization. There's also the opportunity in this dilational zone for the fluid to undergo relatively rapid changes in physiochemical characteristics to drive gold precipitation. In the Bendigo zone, we see preservation for these systems is relatively high because of the tectonic quiescence that's occurred between 400 and 65 MA. Yes, unfortunately, some of the orogenic gold systems have been eroded, but progressive uplift and erosion over this time has brought these world-class gold systems relatively close to surface. We won't dwell on the large-scale tectonic triggers, but again, the 3 major back arc inversion events related to changes in far-field subduction arrangement to the east occurred at 445 MA with the Benambran orogeny, at 415 MA with the Bindian orogeny, and 390 MA with the Tabaraba orogeny. Cumulatively, these events generated a 70% crustal shortening. This has mostly been accommodated in the formation of that V-shaped geometry across the Stool and Bendigo zones between the Delamere orogeny and the Selwyn block. Gold production from the Bendigo zone has mostly been focused above the Mount William fault, which represent the boundary between the Bendigo zone and the Selwyn block, and the Melbourne zone above the Selwyn block. Moving on to a smaller scale, we see that there's a progressive structure change in structural deformation is preserved in the rocks. So we actually go from low bedding parallel flexural slip and open folds to progressive tightening of these folds. When they continue to develop, they actually get locked up under continued compression. And during that, there's a failure in a series of low angle displacement faults cross-cut fold hinges. Those are those key structural sites for mineralisation because they are linked by a fracture mesh that is permeable during periods of fluid overpressure. Within the Castlemaine group itself, rheological contrast between the lithologies in the turbidites enhance this network, but also they make it more irregular. And we can see that the highest periods of fluid flux coincide with the shortening events. GSV work has identified that gold mineralisation more likely took place away from major intrazonal faults related to more second order and third order structures that are characterised by a single major phase of deformation, slaty and no crenulation cleavage, upright, non-rotated axial planar folds with sub-horizontal fold axes, and that's in contrast to more polydeformed rocks that you might see closer to those major scale structures. If we examine known areas of gold mineralisation, we can clearly say that high-grade gold mineralisation is co-located where these third-order faults refract from bedding parallel into more horizontal positions, and that occurs in relation where they start interacting with fold closures. Considering fluid source, we can see that during the tectonic events, it's relatively easy to generate lots of fluid during prograde metamorphism. The transition from green schist to amphibolite facies is at 550 degrees C, and that's characterized by the formation of amphiboles from chlorite, so that generates lots of water. And we can see that that's 100% temperature controlled and independent of pressure. So it's pretty easy to consider how under these temperature conditions, we can generate voluminous, aqueous, low salinity fluids. And we see these fluids preserved across all the Victorian orogenic gold systems. We also see a lot of CO2 in these fluids, and that can be explained by the breakdown of carbonates just above the transition from green schist to amphibolite grade conditions. Given the similarities of some of these fluids that we see in the deposits across Victoria, some extra work's been done in terms of examining the fluid sources using noble gas and halogen analyses. And this work was completed as GSV Gold Undercover project. On the left, we see a plot of 36 argon over the ratio of 40 argon to 36 argon. So this ratio down here actually helps us distinguish between air-saturated water, which goes down here, and metamorphic fluid. So we can see that most of them plot away, in fact, all of them plot away from air-saturated water. So we're comfortable that there's metamorphic fluids involved. And then just the 36 argon concentration actually is a function of the carbon dioxide, water, H2O in both the fluid and the source lithologies, but also a measure of fluid rock interaction. And we see a few different things going on here. One thing of note is that this is the box for fossil here, and that maybe that tells us something about how there were more processes there that might have generated gold deposition than at other deposits, and that might help us explain some of the extreme gold grades that we see in that deposit. On the right, we see halogens, which are a tracer of salinity. Even though they're low salinity, they've still got some salinity, and we see major differences between deposits in the west and the east. So this box here, this is Stall, and those low iodine chlorine concentration ratios relate to interaction of the fluids with metabasalts, which are co-located with mineralisation at Stall. As we progress into the Bendigo zone, we see that influence less and less, but what we do see is a transition, especially into the Melbourne zone, into high iodine chlorine ratios, which demonstrates that there's been an interaction of those fluids with organic rich sediments which dominate the stratigraphy in the Melbourne zone. When we examine potential gold sources, the metabasalts and the metacentrum rocks of the Castlemaine group could both be plausible sources of gold. When we use global averages for similar rocks from similar tectonic settings, we see that basalts have slightly less gold, around 5 ppb, compared with sandstones and shales. In turn, shales are a bit more enriched in gold compared with the sandstone. This means that a relatively small zones of carbonaceous material, such as these preserved here, could be important metal reservoirs in Victorian orogenic gold systems. And moreover, that shales, and to a lesser extent sandstones, could also be the source of arsenic, given their relatively high concentrations compared with the basalts. And arsenic is considered an important pathfinder in these orogenic systems. We can use the study of Thomas et al., who looked at laser ablation element mapping of pyrites across the Bendigo zone deposits to illustrate evidence of gold and arsenic being removed from diagenetic pyrites. Here we've got a plot of mean gold and arsenic in pyrites of various parageneses from across the Bendigo system. Note that there's a log system. Diagenetic pyrite has a mean value of 0.6 ppm gold and 1300 ppm arsenic. When diagenetic pyrites have been affected by metamorphism and desulfidized to pyrrhotite, we can see that pyrrhotite would plot, the pyrrhotite mean compositions would plot somewhere down here. So they'd have a content, a gold content of 0.04 ppm and a mean arsenic content of 4 ppm. So that means over 93% of the gold and 99.9% of the arsenic has been removed from this pyrite to pyrrhotite transition. It's actually pretty remarkable that a geological process could be that efficient. Then if we look out, we can see, look as we pass into gold-bearing reefs, we actually see that the arsenic and gold contents in the pyrites as we move towards the mineralized zone increases. And that ultimately, when we reach the gold-bearing reefs, we see that gold is 9 times enriched in the pyrite in the gold-bearing reefs compared with the original diagenetic pyrite. So what we're actually seeing here is mapping out the actual potential of gold mobility in Victorian orogenic gold systems. So we've seen that diagenetic pyrites most likely hosting carbonaceous shale could provide an important source of the gold. However, no comparable studies exist for the matter basalts. That's work that GSV is just starting on now. So if we consider the regional stratigraphic setting in the Castlemaine group is less than 5% black shale, and in certain areas, especially in the southern portion of the Bendigo zone, goldfields are hosted in sequences that are largely dominated by sand. It's hard to actually imagine how we can only appeal to stripping of gold from diagenetic pyrites to be the only source of metal in these deposits. And if we look further afield, we can see that whilst not only is there a large thickness of metabasalts, and that's what this is a map of here, we see a lot of the gold deposits are co-located with those large thicknesses or just to the edge of. When we also compare the stratigraphy in the Castlemaine group with that of the Melbourne zone and the Tabarabra zone, which have had far less historic gold production, we can actually see that there's the stratigraphy there is almost completely dominated by black shales. So that's something we're having to work through, that does that order of magnitude less historic gold production, does that relate to the relatively underexplored nature of the Tabarabra zone, or does it relate to differences like things in metamorphic grade and availability of fluids? Sulfur is considered key in the orogenic gold systems because it's widely considered that gold is transported in these systems by sulfide and bisulfide complexes, and that can explain the lack of base metals in these systems because those will be transported by chloride complexes. If we recall that the major fluid release is temperature dependent and occurs at the green schist to amphibolite metamorphic grade transition, and that's associated with the desulfidization of pyrite to pyrrhotite, also occurs around this temperature. We can see that that's probably also providing the likely source of sulfur in these systems. We can see, if we look on here, this is the bulk sulfide signatures for orogenic gold systems across Victoria, and we can see that they range from +5 to -5 per mil, and that's pretty typical as either being sourced from diagenetic sulfides and or magmatic rocks. So we can't really distinguish between either one. If we look on the right-hand side, we can look at the work of Tompkins et al., who looked at the sulfur mobility windows for peelites under a range of PT conditions and metabasalts as well. And we can see there's a much larger range of sulfur producing window in there, which might point to the Castlemaine group being the more likely source of sulfur. In simple terms, gold is precipitated in those structural traps that generate rapid physiochemical changes that are brought around by rapid depressurization. But what does that rapid depressurization drive in terms of PT conditions, but also other physiochemical parameters that may generate gold precipitation? On the bottom left here, we have an FO2 pH slide. We see that gold is most soluble under near neutral pH, just below the sulfate boundary, and across both sulfide and bisulfide complex stability fields. If we look at how tightly packed these contours are, we see the quickest way to form gold is an increase, to precipitate gold is an increase in FO2. But we don't see a bunch of sulfates preserved in the systems in Victoria, unlike deposits elsewhere. So in terms of other changes, near neutral pH can shift in both directions to generate gold precipitation. And we can also see temperature drops, such as here. It's really hard to transport gold in sulfide or bisulfide complexes below 200 degrees C. We can also see that simple decreases in sulfide complexes in activity can also precipitate gold. We can precipitate through pyrite formation, and we can also precipitate through chemisorption reactions that slightly lower the FO2 and generate arsenopyrite hosted gold. In addition, we can look at the rocks to actually understand what is happening in the sites of gold precipitation. We can see phase separation as evidenced in fluid inclusions in liquid vapor ratios, the CO2 content of the fluids. So CO2 mixing in these dilation sites would lower the pH and make gold bearing complexes unstable. And similarly, the fluid could interact with a reductant through wall rock reactions in order to allow gold to precipitate. And we can examine the likely scenarios that are important for Victorian orogenic systems by actually looking at the rocks for clues. And we can see that high aluminium phengitic muscovite associated with quartz pyrite assemblages across gold systems in Victoria are seen in this sodium aluminium, potassium aluminium plot. And that's evidence for slightly acidic hydrothermal fluid, which is associated with alteration related to gold mineralization. So that's saying that pH changes are an important factor in gold precipitation. We also see a lot of evidence for CO2 unmixing from the fluid, and that's preserved as veinlets and spotting in mineralized zones and in the wall rock. And just quickly, because we're really short on time, the three events responsible for gold mobility, just in terms of those tectonic events, has also been responsible for the progressive unroofing of the Bendigo zone and its rocks and gold mineral systems from the Devonian. And this has brought the gold orogenic systems closer to surface. Since the Devonian, the Lachlan Fold Belt has been largely cratonized, so it's been relatively stable until the Cretaceous, when further uplift and erosion between that time and the Pliocene partially eroded the orogenic systems that generated the alluvial gold fields across Victoria. And if we think about geochemical dispersion for a moment, that might help us more readily identify gold gold mineralisation. We can see that arsenic is the most mobile in the near surface environments, followed by antimony, and this schematic demonstrates the relative size of that dispersion may be in excess of 10 kilometres from known areas of gold mineralisation in Victoria. And I think I'll leave it there and save any questions for the panel Q&A, or feel free to email me on this email address. Thank you very much for your time.